This video is a thoughtful expansion on our previous video on wall bracing versus shear walls, which has received very insightful feedback and important questions from viewers, highlighting the need for a more comprehensive explanation that is carefully crafted to reach a wider audience. In response, we've developed this expanded video to provide greater clarity and depth. Our goal is to revisit the topic and approach it in a more accessible way so as to address common misconceptions, explain fundamental concepts, and provide meaningful distinctions between braced walls and shear walls, both in principle and in application. In modern building codes adopted in most U.S. jurisdictions, the term wall bracing is almost exclusively used in light frame wood construction. However, the term shear wall is used for both light frame wood construction, cold-formed steel, concrete, and masonry construction. Since it would not make sense to compare light frame wood-braced walls with concrete shear walls, we will restrict our discussion to light frame wood construction. The design of any residential structure begins with the architectural layout of the floor and the roof. The structural design is built on the architectural layout and is intended to provide the means by which framing members will resist the loads that they will be exposed to. For a typical residential structure, these loads may be broadly classified into two groups. The first group consists of vertical loads. These are loads that are primarily acting vertically downwards. Typical vertical loads include dead loads, which is the weight of the building materials. We also have live loads, which is the weight of the occupants, furniture, and other non-permanent elements in a building. Other vertical loads include wind uplift loads, which act vertically upwards and develop at the roof when internal pressures are higher than external pressures. The second group are lateral loads. These are loads that act laterally on a building and include seismic loads and wind loads. Other lateral loads include soil loads, which are resisted by retaining walls. As we shall see, both shear walls and braced walls are used to resist lateral loads such as seismic loads and wind loads. In order to understand how shear walls and braced walls resist lateral loads, let us look at their physical makeup. In wood framing, braced walls and shear walls consist of several primary components. First, we have the wood framework of the wall. This will typically consist of 2x4 or 2x6 wood studs spaced at 16 inches on center or 24 inches on center. The next item is the stiff material that is attached to the wall studs. Stiff materials that are used include wood structural panels, gypsum board, cement plaster, structural fiberboard sheathing or particle board sheathing. Thirdly, we have the nails or screws that attach the stiff materials to the wood framework. These consist of edge nailing, which is nailing provided along the boundaries, and field nailing, which is nailing provided on the interior portions to attach the sheathing to the stud. The fourth primary components are the anchor bolts at the sill plate. These are provided to attach the wall to the foundations to ensure that the wall is not displaced by lateral loads. Other components that occur in some shear walls and braced walls include holdowns at the end members and steel straps at the corners of openings. Holdowns prevent overturning of shear walls and braced walls and are only used on selected shear walls and braced walls that are likely to have significant overturning demands. These are the structural components of both shear walls and braced walls. Let us pause for a moment and explore the similarities between these systems. If you went to the construction site of a single-family home and looked at one of the wall segments that is at least 4 feet in length with 2x4 studs at 16 inches on center and wood structural panels with edge nailing at 6 inches on center, you would not be able to know if it is a shear wall or braced wall. This similarity is not limited to wood structural panels. Both shear walls and braced walls can be sheathed with gypsum board, cement plaster, structural fiberboard sheathing, or particle board sheathing. What if the wood structural panel shear wall had edge nailing at 4 inches on center instead of 6 inches on center and also had holdowns? Again, this could be a shear wall or a braced wall. Braced wall methods such as alternate braced walls, also known as method ABW, require holdowns and also require nailing at 4 inches on center when used at the first story of a 2-story building. Additionally, even for braced wall methods that require minimum edge nailing at 6 inches on center, a conservative nailing at 4 inches on center that is applied uniformly along with holdowns would likely not be prohibited. What if nailing was at 2 inches on center? Then there are high chances that this is a shear wall and not a braced wall. While it may be beneficial to the overall performance of the building, use of edge nailing spaced at 2 inches on center for wall bracing prescribed to use minimum edge nailing at 6 inches on center does not benefit the wall bracing design process. Therefore, a wall bracing designer will likely use the nailing regimen described in the code, which means that if you see edge nailing at 2 inches on center, then this is likely a shear wall. When considering nailing requirements and length requirements, there is a point where shear walls begin to stand out from braced walls in terms of construction. However, any effort to distinguish them based on construction materials does not provide a reliable basis for classification. What we are saying is that when it comes to distinguishing between a braced wall and shear wall, the key differences are not captured by the construction materials but by the underlying principles that govern the lateral design of the building. This is where we will find the major differences between shear walls and braced walls. In addition to having similar components, we have said that shear walls and braced walls also perform the same essential function. They resist lateral loads caused by wind and earthquakes. Without any sheathing, a wood framework offers very little resistance to these forces. Even a small lateral load can cause the frame to rack or deform significantly. However, when stiff materials such as wood structural panels are attached to the frame, the system gains lateral strength and stiffness. This reinforcement enables both shear walls and braced walls to maintain the building's shape and stability when subjected to typical lateral loads throughout its lifetime. Therefore, we have seen that at this fundamental level, the two systems are similar in their makeup and function. We are now ready to go into the principles and frameworks that distinguish the two systems. When a designer commences with the structural design of a wood-framed residential structure to resist lateral loads, the first question on their mind is the option between using braced walls or shear walls. Choosing any one of these two options will take each of them on a different path where the outcome may be undistinguishable in terms of construction materials but have extreme differences in the overall layout of the system. Let us assume we have two independent designers. Designer A has decided to use braced walls and Designer B has decided to use shear walls. Let us start with Designer A. The first implication of choosing to use braced walls is the requirement to use accepted conventional construction provisions for braced walls. The most recognized provisions for braced wall design are provided in the International Residential Code or IRC, which is adopted in most states across the United States. These provisions are found in Chapter 6 of the IRC or local building codes, which are based on the IRC. For example, a designer in California will use Chapter 6 of the California Residential Code, which is based on the International Residential Code. If Designer A is familiar with the wall bracing provisions of the IRC and the structure is not located in a region where the ultimate wind speeds and the risk associated with seismic hazards do not exceed the limitations for conventional construction, then the designer can proceed with the design of the braced walls. Let us now consider Designer B, who has opted to use shear walls. The implication of this choice is the requirements to design the shear walls according to accepted engineering practice based on the International Building Code or IBC or local building codes, which in most cases are based on the IBC. A designer in California will use the California Building Code or CBC, which is based on the IBC. When the code says that shear walls shall be designed according to accepted engineering practice, this means that they will need to be designed by or under the responsible charge of a licensed civil engineer or architect. The design calculations and drawings will need to be stamped and signed by an engineer or architect. The implication of all this is that if designer B is not a licensed architect or engineer, then they must hire an architect or engineer to design the shear walls. So we can see from the outset that a clear distinction emerges on the framework that is used to direct the design process. Braced walls design is directed by the provisions in the IRC, while shear wall design is directed by the provisions of the IBC, which require design according to accepted engineering practice. The next step for designer A is to choose the bracing method or methods that will be used to resist lateral loads. IRC wall bracing methods are essentially pre-engineered prescriptive systems, which means that they've been validated by engineering principles and testing and can be used without site-specific structural calculations, provided the building meets the IRC's scope. Bracing methods are largely distinguished by the stiff materials that are used, by the length of the bracing panels, and by the extents of the bracing application. The IRC provides 16 bracing methods, but we will focus on wood structural panel-based methods so that we can accurately compare them to wood shear walls, which are the most common types of shear walls. One bracing method that does not use wood structural panels but is very common is method GB, which uses 1/2 inch thick gypsum board and nailing at 7 inches on center. Please note that the IBC, through reference standards for wood construction, also permits gypsum board shear walls, which are similar to method GB. Gypsum board shear walls do not offer equivalent strength and stiffness to wood structural panel shear walls, and most engineers prefer to use wood structural panels in design. Therefore, we will focus on bracing methods that are based on wood structural panels. The choice to use wood structural panels leads designer A to select between two options. The first option is method WSP, where WSP stands for wood structural panels, and the second option is the continuously sheathed WSP bracing method. Both methods utilize minimum 3/8 inch thick wood structural panels with 8-penny common nails spaced at 6 inches on the edges and 12 inches in the field. Method WSP requires the designer to provide minimum 4-foot panels. Additionally, the code requires bracing panels to be spaced no more than 20 feet from edge to edge and to be provided at the end of braced wall lines, which are imaginary lines associated with the wall segments where bracing will be provided. For continuously sheathed WSP, the code requires the application of wood structural panels across the entire wall line with the requirement that a certain minimum length be provided adjacent openings. Once the designer decides on the bracing method, the next step is to lay out the braced wall lines based on the rules of their placement and then to use their lengths and spacing to determine the amount of bracing that is needed from tables that are provided in the IRC. Therefore, we can see that the design of braced walls is based on rules or prescriptive guidelines that must be followed for the system to work as intended. For demonstration, let us assume that designer A wants to lay out the bracing in the structure shown. Let us assume they are using method WSP and that the building is in seismic design category D2, which is a high seismic area. The next step will be for the designer to lay out the braced wall lines. Braced wall lines are imaginary lines that are drawn along the wall lines where bracing is intended to be provided. For this project, the IRC provides limitations on the placement of such braced wall lines. For a high seismic area such as seismic design category D2, the designer is limited to a braced wall line spacing of 25 feet but may go up to 35 feet if conditions described in Table R 602.10.1.3 of the International Residential Code are met. Let us consider the north to south direction. Since braced walls track actual walls, the designer will first place the two braced walls shown. If a wall line has slightly offset segments, the braced wall line may be placed between them. Only wall panels that are not more than 4 feet from the braced wall line will count as part of that braced wall line. The two braced wall lines are spaced at 40 feet apart. This is not permitted. We said that according to the bracing rules in the International Residential Code, the spacing of braced wall lines in a high seismic area is limited to 25 feet but may go up to 35 feet under certain conditions. The designer must therefore place another interior braced wall line so that the maximum spacing will not exceed 25 feet or 35 feet under certain conditions. At this point, the designer is facing another problem. The code requires bracing at the end of a braced wall line or at no more than 10 feet from the end of a braced wall line if certain conditions are met. Therefore, if an interior braced wall line is to be provided, then a physical wall must at least start not more than 10 feet away. In this case, the designer provides braced wall line B and then provides a short wall segment at the dining area to ensure that the requirement for providing bracing not more than 10 feet from the end of a braced wall line is met. This means that the wall at bedroom 2 and the new wall at the dining area will now be considered for the application of bracing and will also require continuous foundations if the project has a slab on grade. The new wall means that the designer has altered the original intent in order to satisfy wall bracing requirements. The next step is to check the amount of bracing required and the placement of bracing panels on the braced wall lines. Let us assume that line A requires 4 feet of method WSP. This may be provided at the north corner as shown. However, the code requires a bracing panel at each end of the braced wall line or requires the layout to meet certain requirements. Therefore, to satisfy this requirement, the designer proceeds to provide another panel at the south end of line A as shown. The code also requires bracing panels not more than 20 feet apart. The two panels are clearly more than 20 feet apart. Therefore, the designer provides a middle 4-foot panel to meet this 20-foot spacing limit requirement. Please note that for method WSP, the panels have to be 4 feet in minimum length. This means that the panels can be more than 4 feet. The designer will do the same at line B, where they may need to add another wall panel if the spacing between the north and south segment exceeds 20 feet. At line C, the design shows a window opening at the north corner. The code requires a braced wall panel at the end of the braced wall line but provides exceptions if certain conditions and requirements are met. Therefore, the designer will need to evaluate the rules, the exceptions, and the design. If the rules and exceptions cannot work with the current design, then the design may need to be altered. This is the design framework within which designer A operates. The designer is confined by a set of rules that mark a rigid boundary that cannot be crossed. In some cases, this may result in an increase in construction cost as more structural elements may be needed to meet the rules as we showed with the additional wall panels and foundations along line B. On the other hand, for simple regular structures, this approach is fairly much simpler to execute and more economical since it does not require design calculations or a licensed design professional such as a civil engineer or architect. We have only considered bracing in the north to south direction. For this project, the designer will also need to consider bracing in the east-west direction. Please note that our goal in this video is to draw contrasts between shear walls and braced walls and not to provide an exhaustive lesson on wall bracing. If you would like a comprehensive lesson on how to design wall bracing according to the IRC, then please check out the Residential Wood Framing Design Series at www.conventionalframing.com. This comprehensive course walks you through the structural design of a full 2-story residence using the prescriptive provisions of the International Residential Code. The course consists of 4 modules including the conventional roof framing module, the floor and deck framing module, the wall and foundation module, and the wall bracing module. Whether you're a contractor looking to streamline your workflow, a designer aiming to master conventional wood framing, or simply a building enthusiast planning your own home, this course is built for you. Please check out www.conventionalframing.com to enroll. Designer B, on the other hand, decided to hire an engineer. Since this is a wood-framed structure, the engineer decides to use shear walls with wood structural panels such as plywood or OSB. An engineered design is based on the requirements of the IBC, which references other more specialized standards for wood construction. The IBC in Section 2306.1 references several standards including the American Wood Council's special design provisions for wind and seismic, which is the primary standard used in the design of wood shear walls by most engineers. This standard provides the nominal capacities of various shear wall systems including shear walls with wood structural panels, gypsum board, structural fiberboard and cement plaster. After deciding to use wood structural panel shear walls, the next step is for the engineer to calculate the total seismic design force acting on the building. This is known as the base shear. The engineer will also calculate the total wind force acting on the structure and base the final design on the highest loads. If the total base shear determined for this building is 3,000 pounds, this force will be applied in the north-south direction as well as the east-west direction. For the north-south direction, the engineer may use line A and line C. There is no limitation placed on an engineered design as far as the spacing of the lines of resistance. This is a major difference between wall bracing design and shear wall design, and it is one of the core advantages of engineering over prescriptive design. For the most part, the engineer can work with the original layout without needing to introduce new lines of resistance and new wall segments as we saw with prescriptive non-engineered design of braced walls. If the base shear is 3,000 pounds, line A will take half this load, which is 1,500 pounds, and line C will take the other half. The engineer then takes the capacity of the shear walls from the special design provisions for wind and seismic and uses it to determine the length needed. This standard provides the engineer access to different capacities based on the spacing of nailing. A shear wall with 8 penny common nails spaced at 4 inches on center at the edges will have a higher capacity compared to a shear wall with nails spaced at 6 inches on center. Similarly, a shear wall with edge nailing at 2 inches on center has a higher capacity than a shear wall with nailing at 4 inches on center. Therefore, whereas wall bracing using method WSP is restricted to wall bracing with edge nailing at 6 inches on center, an engineer designing shear walls has access to higher capacities for the same length by using tighter nailing. If a wall line has a lot of openings and minimal fully framed segments for shear walls, the engineer can use a high-capacity shear wall with tight nail spacing on one section of the wall line and is not limited by spacing rules between shear walls. The engineer is also not required to provide a minimum number of shear walls within a given line or at particular locations. This provides the engineer with greater flexibility to customize the design to align with the architectural concept. We must mention that there are bracing methods that allow for shorter length of braced walls with tighter nailing, such as alternate braced walls and portal frames with holdowns. However, these bracing methods are limited to providing an equivalent strength to a 4-foot method WSP panel and are still required to comply with the same spacing rules and location requirements. For the layout that we are considering, the engineer may decide to use only one 4-foot panel with edge nailing at 4 inches on center, and that will be sufficient. Such a shear wall will also need holdowns to prevent overturning. We must mention here that the engineer is not required to provide a shear wall along line A. The engineer may decide to use the wall segment at the left side of bedroom 2 and design the system to deliver the forces to this location. In this case, the north-south forces will be resisted by the shear wall at bedroom 2 and another shear wall at bedroom 1 or the living room area. The engineer is only limited by his or her ability to justify the intent of his or her design using accepted engineering methods. On the contrary, for wall bracing, the designer is limited by the prescriptive rules and guidelines that govern the wall bracing design process. That being said, a designer with a thorough knowledge of the wall bracing design process will be able to exercise a lot of creativity even within the limitations that describe the wall bracing process. While we have illustrated some of the core differences in the design of braced walls versus shear walls, there remain critical distinctions worth expanding upon. There are some that were touched on but merit deeper exploration, and others that are more nuanced and may not have been directly captured in our discussion so far. Together, these differences speak to where and how each system can be used, with significant implications for architectural flexibility, code compliance, and overall building performance. One of the most notable differences lies in the flexibility of layout and architectural freedom. We have demonstrated this difference in the example that we have looked at. Wall bracing, as prescribed in the IRC, tends to favor more compartmentalized layouts. It requires a minimum amount of bracing distributed along multiple wall lines, and this usually translates to more solid wall segments throughout the structure. As a result, designs that rely heavily on open concept spaces or large window openings often struggle to meet IRC bracing requirements without added walls or adjustments to the floor plan. In contrast, engineered shear wall systems that are designed under the IBC offer far greater flexibility. Because they are tailored to specific loads and conditions, shear walls can be strategically concentrated in fewer locations. This allows designers to preserve large openings, accommodate unconventional geometries, and pursue more ambitious architectural ideas without compromising structural integrity. This becomes especially valuable during additions or alterations, where targeted structural reinforcement can reduce the need for extensive modifications throughout the building. On the contrary, this is much harder to achieve under the prescriptive braced wall provisions of the IRC, which rely on more uniformly distributed resistance and stricter alignment with braced wall lines. Closely related to this is the issue of regular geometry and spacing rules. IRC bracing depends on the concept of braced wall lines, which must be provided at defined intervals. As we have shown in the example, the code typically limits the spacing between these lines to 25 feet in high seismic areas, but the limit can go up to 35 feet under certain conditions. Additionally, each line must have enough braced panels distributed along it, with specific requirements for panel lengths and placement near ends of walls. These rules assume a certain regularity in building shape and layout, and they break down when buildings become more complex or irregular in form. On the other hand, engineered shear wall design is not bound by such rigid spacing criteria. It allows the engineer to assess the building as a whole, accounting for torsional effects, diaphragm flexibility, and load eccentricity. These are factors that fall outside the prescriptive approach of the IRC and are instead handled through engineering analysis. This makes shear wall design more suitable for buildings with non-rectangular footprints, offset wall lines, or varying story heights. Another important distinction between the two systems are the overall limitations placed on wall bracing. The IRC bracing provisions are limited in scope. They apply only to detached 1- and 2-family dwellings and townhouses of up to 3 stories. As far as the loading is concerned, the provisions are also limited to wind speeds not exceeding 140 miles per hour and cannot be used in irregular buildings in very high seismic areas. In states like California, a 3-story building designed using braced walls needs to be stamped and signed by an engineer. If the same 3-story building is in seismic design category D2, then it must be designed according to accepted engineering practice. Use of wall bracing provisions also includes limitations on building heights, material weights, and is prohibited when the structure integrates concrete or masonry wall construction with the exception of fireplaces, chimneys, and masonry veneer. We cannot conclude this video without discussing why wall bracing is structured around rules that do not apply to engineered designs. A key reason braced wall design under the IRC is governed by strict uniform rules that do not apply to shear wall design under the IBC lies in the fundamental difference between prescriptive and performance-based approaches. The IRC provides a prescriptive path intended for typical low-rise residential structures, enabling designers and builders to comply without performing structural calculations. To ensure adequate performance across a wide range of conditions, the code imposes standardized requirements on wall lengths, spacing of braced wall lines, allowable materials, and building geometry. These rules are intentionally conservative and assume regular load paths, limited building height, and predictable loading conditions. In contrast, engineered shear wall design under the IBC follows a performance-based framework. The engineer of record evaluates the unique characteristics of the building, including geometry, openings, material properties, and applied loads, and designs the shear walls accordingly. This flexibility allows the design to adapt to more complex configurations, such as open floor plans or high-load regions, but it shifts the burden of ensuring structural adequacy from the code to the engineer. Simply put, the prescriptive IRC system relies on fixed assumptions to maintain safety without analysis, while engineered design offers greater freedom because it is supported by calculations that are tailored to the specific characteristics and needs of the building. Thanks for watching, and if you found this video helpful, be sure to like, subscribe, and stay tuned for more insights into wood framing.